Next, let's look at dealing with quadratic functions that are written in vertex form. We're going to practice how to rewrite these in standard form by completing the square. In this first example, we have f of x or y is equal to 3 times x squared plus 6 times x minus 4. In order to write this in standard form, my goal is to write it as f of x is equal to a times x minus h quantity squared plus k. So how exactly do we do this? First, I'm going to take that negative 4 and just push it off to the side and treat that as k. So I'm going to write this as 3x squared plus 6x, and then I'm going to leave a little blank here, and then I'm just going to push off the negative 4 off to the right. Next, I'm going to factor a 3 from those first two terms. So I'm going to write this as 3 times x squared plus 2x, and again, I'm going to leave a blank here, and I'm going to keep pushing that negative 4 off to the side. Now, to complete the square inside the parentheses, I'm only looking at this trinomial x squared plus 2x plus blank. The process is I'm going to divide the middle coefficient 2 by 2 and then square. 2 divided by 2 is 1, and 1 squared is 1. So I'm going to add 1 here to complete the square. However, now I have the two sides of the equation unbalanced because I've just added some quantity. So I'm going to have to subtract it back out to restore the original balance. It looks like I have added 1, but in fact, I've really added 3 because the 1 is being multiplied by the 3 out front. So if I've added 3, the way to correct this is to subtract 3 back out so that the net change is 0. So what have I actually done here? I really have 3 times a square of a binomial minus 7. What is x squared plus 2x plus 1 in factored form? That is x plus 1 quantity squared. This is why we call this process completing the square. Now I have f of x written in the desired standard form. Here we have that a is equal to 3, which by the way matches the same a in vertex form and always will. I now have that h is a negative 1. Remember that we're subtracting from x, so we're subtracting a negative 1 to get that positive 1 addition. And then we also have that k is negative 7. Now that I have the equation in standard form, I can do much of the similar steps as I did in the previous two examples. Let's start with the vertex. The vertex is at h comma k, or in this case, it'll be negative 1 comma negative 7. The axis of symmetry will be the vertical line x equals negative 1. Because a is positive, the parabola will be opening up. Let's add this information to the graph for now. Starting with the vertex at negative 1 comma negative 7. Let's add that axis of symmetry as a dashed line passing through that vertex. This is our mirror. Now let's solve for the x and the y intercepts algebraically. So first I'm going to set y equal to 0 and solve for x. So we have 0 is equal to 3 times x plus 1 quantity squared minus 7. Adding 7 to both sides, we get 7 is equal to 3 times x plus 1 quantity squared. Then dividing both sides by 3, we get 7/3 is equal to x plus 1 quantity squared. And then using the square root property, I get that plus or minus the square root of 7/3 is equal to x plus 1. And finally, subtracting 1 from both sides, we get that -1 plus or minus the square root of 7/3 is equal to x. Now that square root of 7/3, it's not in its most simplified form, but we can keep that for now. The correct simplified form would be square root of 21 over 3. But we have two x-intercepts here, -1 plus square root of 7/3 comma 0, and -1 minus square root of 7/3 comma 0. This is actually going to be pretty tough to approximate mentally into the graph, so I suggest using a calculator to find a decimal approximation for these numbers. Next, let's solve for the y-intercept. So we're going to set x equal to 0 and solve for y. Well, we could do this in one of two ways. We can substitute 0 for x in this new equation that we found, or we can use the original equation written in vertex form. It doesn't matter. The vertex form might make it a little easier though. So we have y equals 3 times 0 squared plus 6 times 0 minus 4. See how easy this was? Y is simply going to equal -4. So the y-intercept will be at the point 0, -4. That one, thank goodness, is a lot easier to find. There it is. And then using symmetry, we can go ahead and create that reflection. Now, for the x-intercepts, we can approximate them, like I said, with a calculator, but you should see that the decimal approximations come pretty close to what you would find by simply connecting the dots. The domain, as always with quadratic functions, is the set of all real numbers. And for the range, we see that the lowest observed y value is a -7, which is included, with no upper limit on the y value. Here I failed to do this, but f of x is equal to 3 times x plus 1 quantity squared minus 7. All right, let's do this process again. I know completing the square can be a little bit cumbersome. In the next example, we have f of x is equal to -1/2 times x squared plus 8 times x minus 1. As we did before, we're going to rewrite this as f of x equals -1/2 x squared plus 8x, and then we're going to leave a little blank and push off the -1 off to the side. Next, I'm going to factor a -1/2 out from the first two terms. So I'm going to write this as -1/2 times x squared. Now, what would we have to multiply -1/2 by to get a positive 8? I think we're going to have to multiply that by a -16. And let's just check our work. If I were to distribute that -1/2, I would get -1/2 times x squared, check. And then -1/2 times -16, yes, that does give me the positive 8 in front of that x. Perfect. Now to complete the square, I'm going to divide the middle coefficient by 2 and then square. So -16 divided by 2 is a -8, and when I square a -8, I get positive 64. So that will be what I add here. Remember that now I have taken an equation that has two sides completely equal to each other, and I've created a lack of balance. I've added a quantity that then has to be subtracted out. In fact, this time I actually subtracted something because that 64 is being multiplied by a -1/2. So in essence, I've subtracted 32 here. So to create the balance that is needed, if I subtracted 32, I'm going to have to add it back in order for the equation to restore its balance. All right, let's go ahead and factor. So we have f of x is equal to -1/2 times X squared minus 16x plus 64 is really x minus 8 quantity squared. And then we have a negative 1 plus 32, so I'm really adding 31 here at the end. So we have three values here that I'm interested in. A is negative 1/2. K here, H rather, is an 8. And K is 31. So let's go ahead and write this in standard form. The vertex is at H comma K, so it will be at the ordered pair 8 comma 31. The axis of symmetry will be the vertical line x equals 8. Because A is negative, the parabola will open down. And now let's solve for the x and the y intercepts algebraically. First, I'm going to set y equal to 0 and solve for x. So we have 0 equals negative 1/2 x minus 8 quantity squared plus 31. I'm going to add the first term to both sides. And I'm going to multiply both sides by 2. Next, I'm going to apply the square root property. So x minus 8 must equal plus or minus the square root of 62. Adding 8 to both sides, we get that x is equal to 8 plus or minus the square root of 62. That means that we have two x-intercepts, 8 plus the square root of 62, comma 0, and 8 minus the square root of 62, comma 0. For the y-intercept, I'm going to set x equal to 0 and solve for y. So I have y equals, and again, I'm going to go back and use the original vertex form just because it should be easier, but you get the same answer either way if you were to use standard form. Y is equal to negative 1/2 times 0 squared plus 8 times 0 minus 1. So we get that y is equal to negative 1. That means that we have one y-intercept at 0, comma, negative 1. The domain, as always, is the set of all real numbers for quadratic functions. And let's see, this parabola is going to open down, which means that the vertex is the highest point. That means the range will go from negative infinity up to, but including 31. So we'll use square brackets for that. Next, let's take a look at the vertex form for the equation of a quadratic function and find out how we can identify the vertex of the parabola without having to rewrite it in standard form. If we have f of x equals to a times x squared plus b times x plus c, we will be able to find the x-coordinate of the vertex without having to complete the square, and that's good news. The x-coordinate is going to be found by negative b divided by 2 times a. In other words, that is going to give me the x-coordinate for the vertex. Once I find that x-coordinate, I simply have to substitute that back into the equation to find the corresponding y value. And that's what this says right here. Substitute whatever x-coordinate you found for the vertex, or in other words, substitute h, back into the equation to solve for k. The axis of symmetry, of course, is the vertical line that passes through that x-coordinate. All right, let's take a look at the first example here to make that connection. So we have the equation f of x is equal to negative x squared minus 2x plus 7. I want to be able to find the vertex without having to complete the square to rewrite this in standard form. First, let's identify the values of a, b, and c. A here, the coefficient of x squared is -1. B is -2. And C is +7. What we just saw is that the vertex has an h coordinate or an x coordinate h equal to -b over 2a. Well, we have -b over 2a. So that's going to be 2 over -2, which gives us a -1 for h. Now we're going to find k, the corresponding y-coordinate for the vertex. For k, we are going to substitute -1 in for x. So we get the opposite of -1, quantity squared, minus 2 times -1 plus 7. Let's be careful with our signs here. -1 when squared is a +1, but the opposite of that is still a -1. Then we have -2 times -1 becomes +2, and then plus 7. So after all is said and done, we get 8 for k. That means that the vertex is at -1, 8. The axis of symmetry will be the vertical line x equals -1. Because a is negative, the parabola will be opening down. Let's solve for the x-intercept algebraically. So if we set y equal to 0, we get, in the original equation, 0 equals -x squared minus 2x plus 7. Now this is prime, not factorable, so I think the only way to solve for x would be to use the quadratic formula. So this might be a good time for you to go back and review the quadratic formula. In the quadratic formula, we have that x is equal to -b plus or minus the square root of b squared minus 4 times a times c, all over 2 times a. All right, let me continue that work here below. So that means x is equal to 2 plus or minus, let's see, that's 4 plus 28, it looks like. So square root of 32, all over a -2. And if I continue simplifying, we get 2 plus or minus 4 square root of 2 over a -2. And finally, I get -1 plus or minus 2 square root of 2. That means we have two x-intercepts, -1 plus 2 square root of 2 comma 0, and -1 minus 2 square root of 2 comma 0. For the y-intercept, I have to set x equal to 0 and solve for y. So I have y equals -0 squared minus 2 times 0 plus 7. So I just get y equals 7. So we have 0, 7 as our y-intercept. The domain for quadratic functions is always the set of all real numbers. And for the range, I see that because the parabola is going to open down, the vertex is the highest point. So the range will go from -infinity up to and including 8. Now let's practice graphing this quadratic function. First, let's start with our vertex at -1, 8. From there, we're going to open down. We have the y-coordinate of the y-intercept at 0, 7. Using symmetry, we'll have another one right beside it. I should always add the axis of symmetry as a guide because a lot of these points can be found by looking at the reflection. Now, for the x-intercepts, -1 plus or minus 2 square root of 2 is actually pretty difficult to estimate by sight alone. So let's find what that is as a decimal.